Good morning, everyone. Welcome to NanoOpen webinar. We have Dr. Muhammed Umar, one of new researcher of the SUNUM family today. Muhammed Umar will briefly discuss his research on developing polymer-based conformable biophotonics and electronics system and their large area application in highly efficient biochemical sensing and displays. Before Dr. Umar starts his presentation, I would like to give you a brief introduction about him. Muhammed Umar received his master's degree in electronics from Quaid-i-Azam University, Pakistan. He completed his PhD from the Department of Applied Physics, Aju University, Republic of Korea. He worked with the Faculty of Engineering and Natural Science, Sabancı University, as a postdoctoral scholar supported by the TÜBİTAK. He is the author of more than 20 peer-reviewed journal and conference papers. His main research interests include biophotonics, wearable electronics, micro-nanomaterial assembly, micro-nanofabrication, and biopolymers. Dear Dr. Umar, welcome to SUNUM again. The stage is yours.
Yeah, thank you. Can I share screen?
Sure.
Okay. Thank you, Noktana, for introducing me. I am Muhammad Umar. I did my bachelor and master's in electronics from Quaid-i-Azam University. And then I did visiting lecturership in Pakistan for a couple of years. And after that, I moved to South Korea for PhD. So I completed my PhD in applied physics from Aju University, South Korea. So my basic research was focused on polymer and hydrogel-based biophotonic and bioelectronic systems and devices for highly efficient bio and chemical sensing and display applications. So I will introduce some of, and then I worked in Faculty of Engineering and Natural Sciences in Sabancı University, where I worked on wearable electronics for biohealth monitoring. So now I am here as a researcher in SUNUM. So I will introduce about the polymer-based conformable biophotonic and electronic system for sensing and display application. That is my work did during my PhD and afterwards. So, so in this, so my presentation is composed of is composed into two categories. Of first one is photonic devices based on the light matter interaction in hydrogels and polymers, where I will discuss about stimuli responsive metal insulator, metal resonators, and random laser from the silk inverse opals. And then the second part is about fully biocompatible, flexible, and transparent bioelectronic component for food quality monitoring. So in the first section, so like light matter interaction in polymer. So what is the light matter interaction? Like if you have a okay. If you have a material where when you incident a light, so if light goes back into the same medium, so this is called a light reflection. So if light is passed through the material and it exits from the other side, so or it travels through the material, so it is called transmission. So if material is like rough, so light could be scattered, light could be spread into different directions. So it is called light scattering. And if this rough material is mixed with some light emitting material, so incident light can generate another light. So that is called the luminescence. So this phenomenon is basically called light matter interaction. So based on the light matter interaction, there are many devices in the real world. So like, for example, based on absorption, like solar cell, based on transmission in telecommunication, based on reflection, you have like surface plasmon resonance devices for bimolecular interaction. And based on light scattering, you have Raman spectroscopy that determines the amount of the nanoparticles and their concentration and the size of the nanoparticles. And based on the emission, so there are some lasers that was based on the light emission. So I will discuss about some reflection and transmission based devices as well as lasing devices from the light matter interaction part. So the first thing I will discuss is the stimuli responsive metal insulator metal Fabry-Perot resonators. So basically, in the photonics, like you have surface enhanced, plasmonic resonator that are used to detect the bimolecular attraction. So in this case, like you measure the interaction of molecules based on the shifted resonance peak of the surface plasmons. So these are also used in the color printing and imaging as well as the color display devices. But the problem with these devices is they are being fabricated with the e-beam lithography. So this means they are very costly devices, and also like they cannot be fabricated on the large area because of the uh, specification of the e-beam instruments. So the other thing could be like metal insulator, metal Fabry-Perot resonator. So they are lithography free. You can make them on your required size of substrate. So this could be found by sandwiching a insulator layer between two metallic films. So two thin metallic films. So there could be two types of resonator. One is the absorber and one is the transmission. So absorber mean if you put a very thick silver layer about 100 nanometer underneath bottom layer, and then top layer is always 30 nanometer in both cases. So if you have a 100 thick bottom silver film, so it is a color absorber. So if the bottom layer is 30 nanometer or thin, so it is called color it transmits the light. So if you see like if the thickness of the insulator layer is increasing, so the resonance peak of the device is also shifting. So this means by tuning the thickness of the insulator layer, we can tune the resonance shift of the device. So in these cases, like this insulator material are rigid. So the in biological sensing, these insulator cannot work because light is localized in this insulator layer. So we cannot use because bioanalyte cannot affect this insulator. Therefore, if we use some hydrogels or stimuli responsive materials, so we can use them as for the biological sensing. So for that, in our work, we use, in this case, we use a photoresist. I will discuss next why we use it, but we sandwich silk, hydratable silk biopolymer between two silver films. So, and then if we see in air, so this is the resonance spectrum of the devices that are fabricated by different thickness of the insulator layer. So if we increase the thickness of insulator layer, we can tune the resonance spectrum. So we fabricated blue, green, and red color absorber in this case by fixing the bottom layer with thick bottom layer, thick silver bottom layer. And then if we put the same structure in the water, so the silk absorbs the water from the environment, and it swells. So it change the physical volume of the hydrogel, and it and change the physical volume of the device as well. So this means so therefore the resonance spectrum shift to the higher wavelength. So this means, and this wavelength tuning is very high. So this means we can use this for the biological sensing purposes. So, and then we characterize it in different at different angle of incident light. So if we change the angle of incident light, the resonance spectrum shift to the lower wavelength. So also in air and in water as well. So So we also simulated the spectrum. So like simulated and experimental results are in the are well matched. So this means these devices are also angle dependent. So if we use this angle dependency of the angle dependent characteristic of these devices to scan the biological surfaces, like we put it on the contact lens and we move the light source, and then we see like at different position, we see the resonance dip is changing to the blue side because of the curvature of this contact lens, as well as we confirm it onto the human brain model. So basically, in the previous slide, we use a photoresist as a sacrificial layer. So we dip the sample in the acetone and remove this sample, and then we confirm it onto the contact lens and brain model. And so this means these devices could be confirmed, and their thickness is just around 400 nanometer. And then we use this device when it was conformed onto the contact lens to measure the glucose concentration in the water solution. So when we put the sample in the glucose solution, so we see like when there was no glucose, so you can see the resonance peak, and when the concentration of glucose was increasing in the water, so the resonance was shifting to the higher wavelength. So this means this could be used to sense the glucose concentration. And then we also check that if like we only change the refractive index of the background, like there is no effect on this on the insulator. So we see like by simulation, we check that there is no effect on the wavelength of the resonator. So this means like silk or like polymer is a basic element in this case. Like so the water is changing the refractive index of the polymer, and also it is increasing the thickness of the polymer. So that are the major effect of major principle of this device. Also, we check like okay, if we are changing the refractive index of the silk in the water, this means like we are adding more glucose, so resonance is shifting from the like 887 to 905 nanometers. So the refractive index sensitivity of 607 nanometer per refractive index unit. So refractive index sensitivity of this device is also very high. And next, we also use the color filters like that transmits the light. So they like absorb other lights, and then they transmit only one light. And we determine the water sensing. We check the water sensing in the different solvents like acetone and IPA. And then we so this so we prepared a different color filter with the different thickness of the top metal layer, like 10, 20, and 30 nanometer. In air, you can see the spectrum, and in water, you can see the shifted spectrum. So in this case, we found that like when you are depositing thin metal film, they have inherent pores. So those inherent pores let the water to penetrate inside the device, and it swells the silk film. So in this case, if like thickness of top layer is 10 nanometer, the response time of the device is very fast. So if like the thickness is increasing, response time getting slow. This is because like if the top metal layer is very thin, so there are there are much more pores, and maybe they could be more bigger. That's why the response time is fast. And then we utilize like in the chemical sensing, like we put the silk film of 90, 120, and 150 nanometer in acetone, and we see like we can measure the minimum 0.2% of acetone in water, and as well as 0.2% water content in acetone, and 0.00 maybe 1%, 0.01% content of water in IPA. So there is difference in the like amount of water sensing in acetone and IPA because of the polarity of solvents, and we think that the acetone can hold, because of the polarity, acetone can hold the water, and IPA can let the water go to the bottom. So also the thickness, whenever we have a thick silk film, so this means silk volume is high and it could be affected by the water more fastly, and it could sense more lower content of the water. So this was this work was based on the silk, and this other work we used we sandwiched another polymer that is I will pronounce is PNIPAM. So this is the basically uh, thermoresponsive polymer. So this polymer has their critical temperature limit to the 37 degree, and they are basically utilized for drug delivery because their critical temperature is near the least critical temperature is near the human body temperature. That's why they are used for drug delivery. And we sandwich this between the two metal films, and then we put the sample in the water. So if we put the sample in the water, so initially at room temperature, this polymer swells. So this means it absorbs water from the environment, and then when we increase the water temperature, so it goes to the so it retracts the water from inside, and the size of the cavity starts shrinking. So the resonance spectrum goes to the lower wavelength. So this is the same. So if we repeat the experiment and if we change the water temperature slowly from higher to lower temperature, so the resonance also goes to the uh, higher wavelength. So this is because of the properties of this utilized polymer. And then we show that this is the by simulation we show how the thickness of the polymer changes with the increase in the temperature. And next, we also made a display device as a thermometer, so we can check the temperature of the room by making a cell that contains water and this color filter. So if we increase the temperature of the room, so the color of the color filter changes because of the retracting water from the polymer. So this means this could be utilized as a display color filter for the room temperature sensing. And then we see that if we bury this, because as I said, that this polymer is changes its resonance depending on the temperature. So if we put when we put it under the chicken tissue and we slightly chicken tissue with the temperature at 26 degrees centigrade, we see the resonance that is exactly same the resonance in the water at 26 degrees centigrade. And also we check some the other temperature of the chicken tissue, so it's behaving same like in the water. So this means this could be like buried in the biological tissues to make to sense the temperature of the to work as a thermometer. So and also we utilize the same sensor. We lift out we use the sacrificial layer and then lift off, and then it was transferred onto the pore skin, and at some temperature it again shows the resonance dip on the biological tissue. And here is the lift-off process. First, we remove it in acetone and then transfer to water, and then we scooped it off on the biological tissue. And then we also showed that this polymer also can be affected with the alcohol. So we checked the amount of alcohol in water. So initially here you can see from 0 to 50%, the response of the response of the device. First, the resonance shift in the water. So this is in the water at with 0% alcohol, and when the alcohol concentration is increasing, the resonance is shifting to the lower wavelength. And when we check, so very low amount of alcohol in water could be sensed, like 0.5%. So this means like until the 15%, so this alcohol like starting collapsing the structure of the polymer, and after that it behaves in an opposite way and it start demixing this polymer. So on the other side, if you see like these are some color display devices. So here you can see like water. So here is water, 0% alcohol. So on the right column, so it's only water. You can see the consistent color, but on the left side, if we increase the amount of alcohol, the color of the filter changes. So this means by seeing the color of this filter, so we can determine the amount of alcohol directly by the naked eyes, so without any instrument. And the other side, if you see, there is only ethanol. So this is alcohol. The color is consistent, but on the other side, we are changing the temperature of water. Again, we can determine the water temperature by naked eyes just by checking the color of this color filter. So this was the first thing that I had to discuss about the stimuli responsive metal insulator metal resonator. So we can choose the specific polymer with specific properties that could be affected by some stimuli. So we can use to scan biological surfaces and color-based thermometer, and also for glucose, water, and alcohol sensing in the organic solvents. So the second part of the my work is some biological laser. So random lasing and amplified spontaneous emission from silk inverse opals. So basically, this is the basic principle of laser. Like we have a cavity and we have gain medium within it, and when we pump, so the gain medium emits the light, and the light can resonate between the cavity, and then when it has enough power to exit the exit from the output side of the cavity, so it exits in the form of lasing. So there are these lasers are these days being utilized in biological application. For example, here you can see a biological laser, cavity laser. So this cavity laser can used uh, uh, to engineer or scan the biological tissue, and also this cavity laser can be utilized for imaging the biological cell. So also, like, there are some sphere-based laser. So they use very high refractive index oil to scan the biological cell, again by emission from the biological cell, by light emission from the biological cell. So this kind of laser, so they are being utilized by the expensive materials, and they require very to make high Q cavities. And also these lasers are not biocompatible, so they could not be utilized in the living creature. So therefore, our target was to fabricate a fully biocompatible laser that could be utilized in the living systems. So we use the random laser. So basically, the random laser is very easy to fabricate. We put some amount of randomly scattered nanoparticle inside the light emitting solution. So if like light is just if we pump this solution, so if light just directly goes through, and it is a spike-free spectrum, so it is called non-resonant or incoherent feedback. So this is called amplified spontaneous emission. Just one photon is amplifying, is creating other photon, and light is just amplifying. But on the other case, if this emitted light form in the form of a loop, so they with the certain wavelength of photon, they combine with other photon, and they emit and they are emitted in the form of some spikes. That is called resonant or coherent feedback. So this is called laser output. So we also utilize similar kind of phenomena to make fully biocompatible lasers. So in this case, we take the silk biopolymer, because silk biopolymer is fully biocompatible, and we use some a dye that is also biocompatible. So sodium fluorescent dye that is also biocompatible, and mixture of silk and sodium fluorescence is a fully biocompatible will be fully biocompatible device. So we make the silk inverse opal by using nanosphere of polystyrene, and and then by removing after making, first we make the polystyrene sphere on a silicone, so they were uniformly assembled, and then we dropcast the solution of silk and sodium fluorescent onto the nanoparticles, and then we etched after drying. We etched those polystyrene particles in the acetone, and we made a three-dimensional photonic structure that is called silk inverse opal. And we see, like in the silk inverse opal, so there are different kind of phenomena, like in this structure. So we can see the lasing. Also, the structure shows the amplified spontaneous emission with the very low input power, and also the amplified spontaneous emission in the film. So this amplified spontaneous emission with low input power is because of this nanostructure in the film. And this lasing is mainly because, like, whenever we are making this device, there could be some inherent cracks in the device. So those cracks make some cavities. So those cavities act as a random lasing platform. So we found that again, like as you see, like in the bulk silk film, we have amplified spontaneous emission, but threshold is very high. But whenever we are adding some PMMA, like polystyrene sphere, so the threshold is getting lower because there is a refractive index mismatch between the polymer and sphere. And when we remove the sphere by using acetone, so these spheres are replaced by the air gaps. So refractive index difference between the in the device is increased, like air refractive index is 1 and this is 1.54. Therefore, we obtain amplified spontaneous emission with very low threshold. And then we find that as I said, like there could be some inherent cavities inside the sample because during the fabrication. So those cavities act as a random lasing platform, and we can see like very sharp spikes in the form of a random laser. So these are we measured at different points. And as well as we check like ordered, if we use uniformly ordered inverse opal. So this means there could be phenomena of photonic band gaps, and those this means the photonic band gaps also can create random lasing in this structure as well. And if we are using disordered structure by mixing different size of the particles, so we could also see the random lasing. So, and then we confirm this lasing by using spatial coherence phenomena. So we utilize double slit, and when there was amplified spontaneous emission, we could not see any light like in the form of fringes. So this means it is just amplified spontaneous emission. And on the other side, when there are lasing peaks, we see this coherence, spatial coherence phenomena. So this spatial coherence phenomena is a basic phenomena to check the light is like coherent or not. So this means our light is coherent. So this phenomena was the random lasing from the silk inverse opal. And then for the application, first we also like to make the silk inverse opal film. We crushed it into the powder form, and then we see again the same phenomena of amplified spontaneous emission and random lasing in air. You can see the lasing picture. And then we utilize this powder and put inside the onion tissue. So we find that this kind of good biological application. So under the onion tissue, we put this powder, and here you can see the spectra UV under the UV light. You can see this the emission color because of the sodium fluorescent. So under the onion tissue, it again like could have amplified spontaneous emission, and also it showed the random lasing. So this means this means that this kind of random laser platform can be utilized to engineer or scan the biological tissues. So also, we utilize this because the sodium fluorescent is pH sensitive. So the hydrochloric acid vapor can quench the PL of the sodium fluorescent. So we see like the amplified spontaneous emission phenomenon decays when we expose the sample to hydrochloric acid vapor for 2 seconds and 4 seconds. So the spectrum decays very fastly. On the other side, the PL-based spectrum, it decays. It takes 20 minutes, 30 minutes to decay to the same level. So this means this kind of silk inverse opal based platform can be utilized for random laser. That could be for random lasing in the biological tissues to scan or engineer the biological tissues, and as well as to sense the hydrochloric acid vapor or some hazardous vapor. So this is the basically summary of this work. So these are the organic diode 3D silk inverse opal structure as a fully biocompatible random lasing platform, and it could use to sense acid vapor, and it could be implantable to the biological tissues. So on the second part of my work is the fully biocompatible, flexible, and transparent bioelectronics component for food quality monitoring. So basically, bioelectronics is electronics in biological systems. So bioelectronics mainly started from the experiment of Luigi Galvani. So where they put some electrostatic charges to the frog, and they find the contraction in the frog muscle. So and after that, bioelectronic flourish. So people are using bioelectronics in a very thin form to extract the signals from the human body, to attach and extract the signal from the human body. So here are some bioelectronics devices. And so these are also like dissolvable bioelectronic devices based on some polymer. But problem is that these are patterned with different materials. So like you have to pattern one material, and the material is on the surface of this devices, surface of the polymer. So our goal is to design a bioelectronic device with seamless biotic and abiotic interfaces. So this means our goal is to make a film that should be conductive, but it should be uniform. It should have uniform surface. So we utilize again silk biopolymer. So I will introduce a little bit about silk. Silk is basically made from it comes from the nature. So caterpillar makes this silk, and this silk fiber. So there are silk fibers. So it has serician and fibron. So serician is 25%, and fibrin is around 75% with different amount of amino acid. So and then this silk fiber could be extracted into the form of solution, and this solution can be processed into different forms. So it could so initially this solution, when we make films or other things, so they have random chains of the amino acid, and then they can be chemically processed into the crystalline form, so in the uniform shape, so a connected chain. So by chemical processing. So, and then when we process this silk, it could be processed into the different forms. So people are making fiber, gel, sponge, tubes, microsphere, and film from this silk, and which could be utilized for the tissue engineering, drug delivery, and as well as wound healing process. So silk is like a polymer, but it has very large application in biomedical field. So therefore, we utilize silk to make our device biocompatible and also transparent. So silk is transparent, so its optical transparency is nearly equal to the optical transparency of the glass. So in this case, we make some electrodes in the form of resistor and antennas, and we put silk onto that. So these electrodes are made from the silver nanowires. So when we put the silk, so these silver nanowires are fully buried inside the silk. And here you can see the pattern. So silk is transparent, and also the silver nanowire part is transparent. So If you see the SEM image on the silicon, we can see the silver nanowires on the silicon and then SEM and AFM images. But when we bury the structure into the silk, so here is the SEM image and this is the AFM image. So this AFM image shows like silver nanowires are fully buried inside the silk, and there is very low roughness of this surface. So this means it could be utilized as a seamless surface for biotic and abiotic interfaces. So here we showed that if we, by changing the concentration or amount of silver nanowire, if we increase the amount of silver nanowire, optical transparency slightly reduces, but we can increase the sheet resistance. So this sheet resistance is similar to the ITO because many electronic devices, wearable electronic devices are based on ITO. So ITO is very expensive. So this silk plus silver nanowire could be a good replacement of ITO-based devices. So, and then after basic characterization, we also check the mechanical stability. So if we have silver nanowire in the silk with different density, so we bend them for 1,000 times each of the sample, and we see there is very slight change in the final resistance after 1,000 time bending. So this is just 1% or 2% change in the sheet resistance of this silk conductive silk film, but there is no change in the optical transparency of the silk. So this means there are no cracks or some no other phenomena happened in the silk. And also we showed that in the if we have an antenna, so after like in the like when it is not bended, so you can see the resonance spectrum of the antenna. So when it is bent, so when it is bent, so resonance spectrum is shifted to the higher wavelength. So this is the multiple bending of the antenna. So this means the recovery of the sample is very good. So this means like after multiple bending, we can, even after multiple bending, it do not affect the silk-based, silk and silver nanowire-based electrodes and antennas. So on the other side, if you see, we show that two silver and silk electrode could be utilized in electronics. So we just turn on an LED by connecting silver nanowire network in the silk. So by applying a voltage of just 2.3 volt, so because of the low conductivity of this electrode, so this means this electrode could be utilized in electronic application. And then for the food quality monitoring, as you know, like silver get corrosive with some gases like hydrogen fluoride. So this means like an odor in the form of hydrogen fluoride from the spoiled meat or chicken can affect the resistance of the silver nanowire. So in this case, we utilize a line resistor and RF antenna to measure the food quality. So when we put this resistor on the spoiled food, so the spoiled food start changing the resistance of the silver nanowire in the silk film. So we can, and on the other side, we also put it on the fresh food. So there is a slight change in case there is slight increase in resistance in the case of fresh food because of the humidity. It can affect the resistance of silver nanowire. And on the other side, the change in the resistance of silver nanowire because of the spoiled food is very high. So this means we can check the quality of food by just putting this sample on the food container, and as well as if we see the response of the antenna, so we can see the decrease in the dip of the antenna wavelength. So this means like this antenna could also be utilized because this dip is decreasing because the resistance of the device is increasing. So we made some simple tests on the glass. So there are silver nanowire coated on the glass. So this is the fresh sample. So if we expose it with the spoiled chicken, we can see the surface is changed because of the corrosion due to the hydrogen fluoride gases. So this was the last part of my presentation. So we utilized patterned silver nanowire network that was buried in silk polymer film to yield a biocompatible, flexible, transparent, and conformable electrodes and antennas, so which could be applied to make electronic components as well as a food sensor. So I would like to thank you everyone for listening.
And thank you, hocam. Now session is open for question. You can just speak up or raise hand, or if you like, write on the chat box. If you have a question about presentation to Muhammed Umar. Any question? Hocam, they thank you on the chat box, and Meryem Fehmi would like to contact you. Can you follow the chat box, hocam?
Yes, hocam.
Muhammed Hocam,
Yes, hocam.
thanks for the nice presentation. So I'm just wondering only one thing, the hydrogel formation. Whenever you create an hydrogel in between silver films. So the first question, how do you make the silver films? This is the first question. And how do you control the thickness?
Okay, this actually we just spin coat this silver nanowire solution on the substrate. Yeah, that's how we, but by like controlling the spin coating speed, we control the density of silver nanowire.
So you buy nanowires and then coat?
Yes, we buy and coat.
All right.
Yeah, and then pattern.
Whenever you, yeah, thanks a lot, Muhammed Hocam. Whenever you create the hydrogel in between the films, if you keep the film distance in between those two film constant by forcing it, because you say, you know, the after hydrogel formation, it is swelling. So if you just diminish that swelling.
Sorry, Oja, I misunderstood. Sorry. You mean the first part?
Yeah.
This one, right? Okay. So this is not the, this is the deposition. This silver is deposition, E-beam deposition.
All right, I got
And
point. So you can control it.
Yeah, and then the silk thickness was controlled by spin coating.
All right, so is there any way to control, you know, the distance in between those two silver film depositions, deposited silvers? So whenever it's, you know, just gets the water, it is swelling, and probably, you know, that distance is getting bigger from your, you know, the slides. But if you keep that distance constant, but still absorbs water, what happens at that point? Have you ever tried that one?
Yeah, we did not try that one, but I think that will create problem for this metal insulator, metal resonator. Like, you mean like if we have silver and then we have silk and then we have some gap, right?
No, you have silver, silk, another silver at the bottom.
Yes.
You still create hydrogel.
Yes.
But
okay.
Whenever you create hydrogel, you have a limited distance in between the films. So that film distance is not changing.
Yes.
So because, you know, after making hydrogel, it is kind of, you know, the expanding and then making a new distance. But if you just control the distance, force it to sit.
Okay. I understand.
Still there is a water, hydrogel, but well-controlled distance.
Mhm.
What do you?
Okay. So you mean just we have two silver films, right? With a
Yeah,
gap.
with
Okay.
a gap, and you make hydrogel of silk in between that gap, but that gap is not changing after forming the hydrogel of silk.
That gap is not changing. We never did this thing, Hoja. Like if gap is not changing, so we could not
But there
sell.
is water. There is
Yeah,
water.
yeah, like rather than silk, right?
You know, silk and water, so it makes hydrogel. Still, it makes hydrogel because there
Yes.
is some, you know, the spaces in between silk. I assume so. So
Mhm.
maybe not huge amount of water will penetrate into the silk,
Mhm.
but still there will be water there.
In that case, Oja, we never did this thing, but in that case, like there should be a nano gap between these two films to make a color filter. So I think it could be uh, difficult, but yeah, maybe it can enhance the sensitivity of the device because the amount of water will be high. So the refractive index of the again device will be more different.
Thanks a lot, Mom.
Yeah, welcome. Anu. Okay.
Any questions?
Yeah.
Then I would like to thank you, Hocam. Thank you for your presentation.
Yeah, thank you everyone.
And thank you all participants for your participation. We will have Emre Keskin next week from Ankara University. He will talk about transforming the agriculture ecosystem through biotechnology, innovation, and entrepreneurship. I hope see you all next week, next Wednesday.
Thank you, Ajay.
Thank you.
Thank you, everyone.
Have a good day.